This is the first lecture on Kuhn. This lecture deals with how Kuhn revolutionized our view of scientific method. And the next lecture will look at how his view of paradigms changed the way we see how the world exists for us and how it's related to language. Thomas Kuhn is probably the most important philosopher of science of the second half of the 20th century. And the Structure of Scientific Revolutions, the book we're reading, is probably one of the most influential books in philosophy of the 20th century. Thomas Kuhn was an effective presenter of the ideas of philosophers who came before him in the first half of the 20th century. Not many of his philosophical arguments or ideas are novel. What was novel was the way he put them together and combined them with a new way of approaching science. The influences on Kuhn and some of his predecessors were logical positivism or logical empiricism, which was the dominant view of how science worked for the first half or so of the 20th century. And it determined the view of science that you're most familiar with, the idea that we have theories or hypotheses and then we test them in experiments. Kuhn is also going to be influenced by many of the philosophers who examined logical positivism and found problems with it. In particular, we'll be looking at a couple arguments from Ludwig Wittgenstein and Willard Van Orman Quine in the second lecture in this unit, as we see how they influence Kuhn's account of how theories in science relate to the world and how theories change and progress from one to the other. So Kuhn's philosophy is best seen as a effect of what happens when science studies itself. One of the most basic ideas of postmodernism is a type of self-reflection or self-reference. When science studies the material world, we can use the scientific method and separate out the relative from the absolute, and we're the observer, and science is the object which is observed, and we try to separate out the objective in the object from the subjective in us. But things are a little bit different when the object that we're studying is also us, as in biological sciences or in psychology or in economics. And in the history of science, or in the philosophy of science, the self-referentiality or the circularity becomes even more pronounced because science is studying itself. And what we're going to be looking at today is the way in which views of scientific method that were based upon the ideas in the first 2 weeks of this course, upon the ancient idea of number and limit, and on the ancient idea of geometrical construction according to rules or according to axioms, and the Enlightenment views of the scientific revolution of purifying the appearances and separating the relative and the absolute. Those gave way when science actually started studying itself, those models of how human reason is supposed to work, and how it should work if it's going to perform its role as the most important part of the human soul and the most important part of human intelligence. They gave way to different views as sociologists and historians of science actually looked at how scientists actually worked in formulating their theories, which wasn't at all the way that the Pythagoreans or Galileo would have thought that human reason ought to work. The first stage in that is going to be logical empiricism. Remember, this was the view that Kuhn set out to refute, or that Kuhn set out to distinguish his new theory from. And it was a theory that arose in the beginning of the 20th century. And the name logical empiricism, or sometimes called positivism, which was the view of the 19th century philosopher and economist or sociologist Auguste Comte, who talked about science as positive inquiry based upon positive facts or experience. So logical empiricism combines two different things: empiricism, or positivism, which is basing it on experience, This would have followed the method of construction that we talked about, where you start with experiences of simple particulars, just like in geometrical construction. You start with points and lines and shapes and put them together to compose larger things. The empiricist gives you the empirical part is the experience that gives you the atoms of experience. The logical part are the rules that allow us to put those atoms together to create larger theories and larger propositions. So the basic idea of logical empiricism is this first item called logical atomism, based upon that method of construction that said you start with atomic ideas, atomic sense data, the most basic simple experiences, and then you use the laws of logic to put those together into theories. The other parts of logical empiricism were used to criticize what the adherents of logical positivism thought were non-scientific, religious, or philosophical, or ideological or political ideas. Logical empiricism was first proposed as a way of settling the types of disagreements that were based on religious and philosophical views that were the source of warfare and of acrimony. So they proposed a verifiability theory of meaning that said that the only things that were scientifically meaningful were things that you could construct from sense experience. The verifiability theory of meaning says things are meaningless which can't be related to some atomic experience or atomic sense data, some experiment or actual fact. And things that failed the verifiable theory of meaning were thought to be mere expressions of emotion, to be merely the expressions of preference or delight or meaningless opinion. So most of the philosophical areas of art and religion and metaphysics couldn't be traced down to anything scientifically, to any scientific fact or experiment or experience. Therefore, they couldn't be constructed in a way that gave them meaning, or scientific meaning. The third element that you see here, the analytic-synthetic distinction, is, for our purposes, it's enough to recognize that it's a fact-theory distinction. You have facts that are observed in experience, and then you have theories that are constructed according to the rules of logic from those experiences. This should sound fairly familiar to you, as the method of geometrical construction that we saw was a basis for all scientific work that came from Aristotle. So in logical atomism, you start by observing things, looking around, more or less unguided, just objectively without any biases or prejudices. You recognize a pattern, you try to form some hypotheses, and then you generalize them to form a theory. You go looking around at the swans, you see that the swan is white, and the swan at the next lake is white, and the swan on the next lake is white, and you come to the general hypothesis or the general theory that all swans are white. Of course, the difficulty with this is that you never know for sure whether all the swans are white unless you check all the swans. You may know that in the 19th century, when people went to Australia, they discovered, in fact, that what they thought was true, that all swans were white, were in fact false, because there were black swans in Australia. So much of the beginning of logical positivism dealt with the logic of confirmation, or the logic of induction. Induction is the logic that moves from particular cases to general theories, unlike the deductive logic that we looked at in Euclid's Elements or in proofs in the method of geometrical construction. So when scientists first looked at how they worked, when they started being scientific about science, they discovered that scientists rarely did that. Scientists rarely just looked around in the world generally without any guidance. One of some of the fields that still use this older method, like the logical atomism, are methods like natural history and biology, or sometimes even the medical profession, because those are still rooted. The medical profession and natural history are based in some of the earlier medieval methods that originate before the scientific revolution. So in natural history, you go out and observe what all of the sparrows do of a certain species, and then you write a little account, assuming that the particular cases that you have studied will characterize the entire species. That's what a natural history would be. And sometimes medical research can work that way as well. You'll do case histories of people's experiences with a certain disease, and then you'll draw general conclusions based upon these separate experiences, separate observations, or stories of the particular cases that you've looked at, and assume that in general things will work the way that they have done in that particular set of theories. Later, we'll talk about probabilistic interpretations of that methodology, where you look at a bunch of cases and then use the logical methods of probability theory to determine when your findings are significant or not. But in most sciences, they found that scientists didn't just observe without any guidance. They found that scientists almost always have a theory or a hypothesis in their mind beforehand, and then it's called the hypothetical deductive method, because you start with a hypothesis and already have a theory about the world. You don't just observe willy-nilly and then form your theory based on observation. Before you do any observing, you already have a theory, and then you use logic to deduce a hypothesis or a prediction from the theory and some other assumptions about how your instruments work and how things, other beliefs you have about how the world is operating. And then, based upon your theory, you deduce a prediction. Then you perform an experiment to test that prediction and see whether your experiment either confirms or denies or falsifies your prediction. I'm sure this is the scientific method that most of you learned about in grade school, when you learned what the scientific method was, of forming a hypothesis, testing it in an experiment, and then seeing whether your hypothesis was confirmed or falsified. The irony is that even though most of you learned that view of scientific method, almost no historian or sociologist or philosopher of science since the publication of Thomas Kuhn's book in 1962 has believed that that is how science actually operates. Instead, it's been replaced by the paradigm theory that we're going to be studying, and despite that fact, the grade school textbooks haven't caught up with the latest ideas about how science actually works. So, unlike the ideas in the hypothetical deductive method, real science is conservative. When sociologists or historians of science looked and saw what scientists actually do, not only did they see that they weren't just looking around and making observations and then putting them together into theories, that they started from a theory and made a hypothesis, but they also saw that most of the time when their experiments came out to be false, when it falsified their prediction, which is what happened most of the time, that scientists didn't abandon their theories. Instead, they kept their theory and assumed that there must be something wrong with how the theory was being applied, with the auxiliary assumptions about the world or their instruments, and instead they kept their theory and took that false experimental result as a puzzle to be solved by altering the theory, by tinkering with it, or by changing what they believed about the rest of the world or about how their instruments or experimental setup was arrived at. Again, they would assume this is part of purifying the appearances. They would assume that there's some impurity in their experimental setup, and they would try to fix their experimental setup until it was purified enough that their hypothesis was capable of giving a prediction that would work in that particular case. So Kuhn's theory thought that science works through paradigms, and a paradigm was a sociological structure a system that guided the operation of a group or a society or a community. So Kuhn thought that scientists work in communities, and instead of being agents who were separate, like the scientific method of separating the relative from the absolute, who were isolated individuals working according to eternal logical principles. Instead, Kuhn thought that scientists work in a community, and the way science works is determined, just like all other social behavior, by the rules and social structures that govern that community. And paradigm was the central concept, he thought, through which scientific communities work. We're reading the second edition of Kuhn's Structure of Scientific Revolutions, which added mainly the postscript, which you're also reading for this week. In Chapter 1, you get the first account that Kuhn gave in the first edition of Paradigms, and there he was kind of unclear about what a paradigm was. Sometimes he would use the word in a specific sense to mean an example, exemplar. That's the common use of the word paradigm. It means a standard example that shows you how to do something. So sometimes he would use it specifically as an exemplar or a particular example of scientific work that guided a community. And sometimes he would use it in a more general sense for the whole wide set of practices and procedures and rules and expectations that guide the science as a scientific community. So the general sense of the term paradigm that Kuhn explained in more detail in the appendix, that'll be your main source for Kuhn's theory of what a paradigm really is. That general sense of a paradigm as a disciplinary matrix includes the particular sense or the specific sense as an exemplar. So a disciplinary matrix just means the matrix of social and behavioral rules and practices that define that social community. So the discipline or scientific community was determined by a set of practices that governed, first of all, the symbolic generalizations, the equations, the laws of nature, the rules that govern them. In the earlier scientific method, they would have identified the entire theory as those symbolic mathematical generalizations that the theory arrived at by generalizing from observations, like Newton's 3 laws of motions would have been his theory of gravity. Now, Kuhn is saying that those mathematical rules or laws that were arrived at by the method of geometrical construction are only a small part of what comprises a discipline or what comprises a paradigm. There are also metaphysical models, which means sort of mental pictures of what reality is that corresponds to those laws. So in physics, we think of atoms as billiard balls. We might think of light as a wave or as a particle. We think of DNA now in a new paradigm of biology as a strand of amino acids that can zip and unzip itself. Or we think of species as sets of populations that interbreed and survive or fail to survive in certain ways. So a metaphysical model are just the mental pictures that scientists make of reality to help them guide their scientific activity. Kuhn also recognized that different sciences and different communities have different values. Sometimes they'll be stated explicitly, like your nursing code of ethics or rules for how to perform an experiment in a chemistry textbook. But sometimes there'll be more implicit values. Implicit means not explicitly stated, in the same way that you have implicit rules about how close you can stand to somebody when you're speaking to them. And oftentimes when you encounter someone from another culture, you notice that it's strange that they're standing too close to you or speaking with their face too close to yours. Those are like different paradigms because they involve different values that aren't explicitly spoken. So, for example, before the scientific revolution, one of the implicit values was that a good scientific theory should be beautiful, should express the regularity of a cosmos, and should be simple and represent the world as a beautifully organized system. Whereas after Galileo, the methods are going to suggest that you can reduce them to mathematical laws that arrive through purifying the appearance and are objective and not relative. So different scientific theories and different paradigms might even have different values that determine whether a work is good or not. We'll see that's going to be a problem for determining when one paradigm or one theory is more true or better than another. Normally we thought that the laws of logic, those imprinted innate rules of logic that Pythagoras talked about, were separate, and we all had the same ones so that we could agree about which work of science was better or worse, which theory was more true or less true. But if the values themselves are part of the paradigm or part of the theory, we'll see there might be difficulty in determining which theory is right, since different paradigms might be employing different values or different judgments about which is correct and which is incorrect. So the objective scientific revolution model that said you can separate the relative from the absolute thought that there was an objective standpoint that had values built into it, rational rules built into it, and that from that objective standpoint you could judge which theory was true or false. We'll see that Kuhn is going to say that the values, when science starts studying itself, we'll see that the values themselves are part of the discipline that's studied. They're part of the paradigm itself, and there is no objective standpoint from which you can judge which paradigm or theory is more correct or less correct. Just in the same way there are rules about what makes a football play good, there are rules about what makes a baseball play good, but there really are no rules that determine how to compare a baseball play against a football play. It's like apples and oranges. The last part of a paradigm are the exemplars. They're, again, the examples that you use to learn what the science is and what makes good science from bad science. So in textbooks in your labs, you all learn to rehearse certain experiments in chemistry, certain dissections in comparative anatomy. Many of you may have learned your anatomy or learned to perform certain nursing procedures on models or mechanical people, plastic models of a person on whom you could practice. So those would be exemplars, standard exercises, standard examples, standard historical problems that you work your way through to learn how the discipline works and what distinguishes good science from bad science. So Kuhn is going to come up with a different view of what makes a science. Kuhn would have said that science only came into existence as a discipline after the scientific revolution, after there came to exist different paradigms and different disciplines that uniformly determined how science should operate. And many scientists today would question whether some fields like economics or even psychology, or some scientists even question whether biology has reached the stage of a real science yet. In pre-normal science, there would be no agreement about what makes a good theory or a bad theory. There would be no rules to govern the values of the discipline. And there would be radically different disagreements about what theories work and what things are the best way of doing that science. And everybody who published in that discipline would have to start from the very beginning to build their science up from the very foundations. So when you look at the beginnings of psychology or you look at the beginnings of economics, you find works of that sort. But normal science is science that already has a single paradigm which is won out and then dominates the field. And in order to be considered a physicist, you have to learn the paradigm of the normal of normal science and physics. You won't be able to get a PhD unless you can complete a research project that follows the rules of that paradigm. So there are going to be guidelines for what counts as successful science, and everyone in that science and that discipline will be doing things correct. And when you find an experiment that falsifies the hypotheses or the theories of that normal science, instead of rejecting that hypothesis, instead that failure will be taken as a puzzle that you'll solve under the guidance of that theory. So science will progress in normal science as a gradual accumulation of puzzles solved. So if you were to get a PhD in science, just as is probably the case in a PhD in nursing, you would find some puzzle or some problem that doesn't quite fit into standard nursing theory, or there would be some prediction, like in the history of astronomy, they found that there were objects in the sky or planets that weren't behaving the way Newton's laws predicted. When they tested the prediction by observation with a telescope, they found that it didn't meet that prediction. Instead of rejecting Newton's laws, they assumed that there must be something else, some impurity in the situation that was preventing the equation from working correctly. And indeed, later scientists solved that puzzle by seeing that there must be other masses out in the solar system, other planets, that were altering the movement of the planets we could observe. And the solution of that puzzle led to the discovery of new planets, which then, when we saw and accounted for those new planets, the predictions would come out correctly. So, according to Kuhn, a scientist never rejects their hypothesis merely because they get a false prediction, because an experiment doesn't accord with their paradigm. The paradigm defines what a science is. A scientist couldn't do science without a paradigm, so they never reject their paradigm unless there's another one already ready for them, unless things have gotten so bad that people are beginning to develop a whole new way of doing that science. So normally science will progress through the accumulation of puzzles, and a puzzle is precisely, according to Kuhn, something that you know has a solution. So when you propose a topic for your PhD thesis in any science, your advisor will check to make sure it's really just a puzzle, that it has a definite solution, and that there are clear methods within the accepted theories for arriving at that solution. So the only thing that would keep you from finishing your PhD and finishing your thesis would be a lack of ingenuity or a lack of expertise in applying the known methods of the field to provide a solution, to provide an extension of the theory, to get a correct prediction where now there's a puzzle, where now there are incorrect predictions. So again, the big difference between Kuhn and previous theories is going to be that whereas logical positivism and the hypothetical deductive method would say when you get a false prediction, you reject that hypothesis, Kuhn is going to say that a false prediction will always lead to you keeping the paradigm. It will be seen as a puzzle to be solved, that you'll have to find some way of fixing your experimental setup or articulating or making slight adjustments to your theory to give the right prediction. Next time we're going to talk about what happens when normal science moves to revolutionary science. So normal science is science according to a paradigm. A paradigm is the whole set of practices that define a science. So normally a paradigm can't be rejected. If you rejected the paradigm, you'd no longer be doing science. Revolutionary science is when a crisis occurs. There are so many predictions that turn out wrong, and there are so many puzzles that it turns out are not really puzzles, and that they can't really be solved using the methods of that paradigm. In that case, people start to come up with a new paradigm, and only when a new paradigm is available is there a transition from one paradigm to another. We'll see that in normal science, science will progress in a straightforward way that everyone agrees with, because there are given rules about how you solve a puzzle, and we'll be able to accumulate more and more puzzles solved. Remember, in revolutionary science, there won't be clear-cut progress, because revolutionary science is going to involve changing all the rules, changing even the very values that determine when you've successfully solved a puzzle and when you can't. And we'll see that Kuhn's most important ideas come from the way in which he claims that in revolutionary science in a change from one paradigm to other. Even the meanings of terms are changed, and even though the way in which we see the world and the way in which we observe through the senses is altered by our paradigm. So in the next lecture, we'll explore Kuhn's claim that members of different paradigms experience a paradigm shift and actually live or exist in a different world, in a different reality, and speak a language which has radically changed and which is incommensurable or untranslatable to the language or the meaning of terms in the original theory. But that'll be the subject matter of the second lecture.